Hi, this is Mrs. Kidman, and in this video, we are going to be discussing angles of elevation and angles of depression. So what do we mean when we talk about angles of elevation and angles of depression? Well, these are angles that we're looking at and specific ways that we could deal with trig. Now, typically when we think of angles of elevation, we're thinking of angles that we're looking up at. So take, for example, this cute little kitten here. This cat is looking up, so its angle that it's looking at that bird at is an angle of elevation. So when they tell you about an angle of elevation, then that's going from the sight level up. So if we had an angle of elevation of 25 degrees, this angle here would be 25 degrees. If it was an angle of elevation of 70 degrees, then this would be 70 degrees. But that's kind of how that angle of elevation works there. On the contrary, we also have the angle of depression. Now, the angle of depression is the view from looking down. So that's kind of what this bird is talking about. Now, a lot of people confuse angle of depression with the opposite angle from the angle of elevation. So our angle of depression is not this angle inside of a right triangle if we were to create one. Our angle of depression is that angle that's created if the object that's looking is looking straight ahead. It's the number of degrees down that they turned their head. So they're looking down. So our angle of depression is actually here. So if we created a right triangle, it would not be the inside angle here, but it would be the complementary of that angle. So if we had an angle of depression of 17 degrees, then what that would mean is the angle at the top of our triangle that it creates here would be 90 minus 17 or 73 degrees. So these angles of elevation and depression are really interesting and really applicable in the real world. This is an opportunity where we use trig and we see these different elements of trigonometry or the study of angles to determine different pieces. So what we're going to do is take an opportunity to study some application questions of angles of elevation and depression where we can use trig in the real world to find different pieces of information. Now, when it comes to word problems on angles of elevation and depression, the most important thing is being able to draw a picture. So as we read through these questions, you'll notice that none of them have an image with them. What I want you to do is sketch an image along with me so that we know what we're talking about here. So let's take a look at this first one. If your distance from the foot of a tower is 20 meters and the angle of elevation is 40 degrees, find the height of the tower. Okay, so what does that mean? Here I am, right here, or whatever we're looking at. And here's this beautiful tower. I don't know what kind of tower we want to draw. I'm going to draw something that looks like this. It's pointed. I don't know, some cute tower. You can make your picture as interesting or as not interesting as you want. It's a tower. But we know from us to this tower is 20 meters. And then we are looking at it this way at an angle of elevation, meaning if these were my eyes, I'm looking up and this angle here is 40 degrees. Now, what we want to do is find the height of the tower. Now, how could we do this? Well, this right here, between our tower and that distance, creates a right angle, right? Beautiful right angle. And what can we do with that right angle? Well, we've now just created a right triangle. And with any right triangle, we can always use trigonometry or trig ratios in order to find other pieces. So we know about this side here, and what we're trying to find is this side here. Now, what are those two sides? Well, this side is opposite our angle, and this side is adjacent our angle. So what I could do is I could use the tangent function, which relates the opposite with the adjacent, in order to calculate what that opposite side is. So let's go ahead and do that. We know that the tangent of angle 40 is the opposite over the adjacent, or the height of the tower over 20. Now, how could I figure out the height of the tower? That's ultimately what we want to do. And this is 20 meters, by the way. Well, what we could do is we could just solve for x. So I'm going to multiply by 20 on both sides to solve for x there. And we end up getting that x is equal to 20 times the tangent of 40 degrees. Now, I know that the tangent of 40 degrees is a number. And as we look at this, if somebody asked you how tall a tower was and you were like, it's 20 times the tangent of 40 degrees, they would be like, cool, how tall is it? So we really want to make sure that we take that next step of figuring out how tall this really is. So as we do the tangent of 40 times 20, we end up getting something that is approximately 16.78 meters. Now you'll notice how I did round that there. We want to make sure that we are rounding our answers to 2 decimal places just to be a little bit more accurate. So that is basically how we would do an angle of elevation or depression. So let's take a look at a couple more examples where we do this. So in this problem, it says you're standing 20 feet away from a tree and you measure the angle of elevation to be 38 degrees. How tall is the tree? This one is so similar to the last one. So here we are, and here's our tree. And our angle of elevation here is 38 degrees, and they tell us that the distance between us and this tree is 20 feet. And so what we want to do is we want to figure out how tall is this tree. Well, guess what? We are given our opposite, we're given our adjacent. So what can we do? Well, let's just use tangent, just like we did before. So the tangent of 38 is going to be equal to the opposite over the adjacent, and we can calculate how tall this tree is. So let's do the tangent of 38. And we end up, or not the tangent of 38, we want to solve for x, so I'm going to multiply by 20 on both sides before I do the tangent of 38. And I get that x equals 20 times the tangent of 38. As we previously discussed, telling someone that something is the tangent of 38 degrees tall really means nothing to someone unless you're a super cool mathematician. So we always want to make sure that we're multiplying this out into our typical digits. So we want to multiply it into feet. And so as we multiply this out, what we end up getting is 15.63 feet. So that's how tall our tree is going to be here. Whoop. 15.63 feet. Awesome. So that's how tall it is. Now that's kind of that angle of elevation. We're looking up. Now let's take a look at this next one where we're standing on the top of the building and looking at a park in the distance. The angle of depression is 53 degrees. If the building you're standing on is 100 feet tall, how far away is the park? And does your height matter? Now notice in these last two problems here how we assumed that this vision started right at the ground. We didn't take into account how tall we are. But really when we're doing problems like these, what we need to be aware of is that this guy isn't looking from his toes. He's looking from his eyes. So depending on how tall he is, we've got to add that height to whatever our tree is. So for example, if this guy was looking and he was 6 feet tall, we would have to add 6 to this. And so really the height of this tree is not 15, but it's 21. You guys kind of see how that works? So let's take a look at seeing exactly how much this makes an impact. So here we are, we're standing on a top of a building, looking at a park in the distance. The angle of depression is 53 degrees. So let's draw our picture here. I'm standing on a building. Look at me go. And there's a park in the distance. Cute. The angle of depression is going to be 53 degrees. Now remember, the angle of depression, based on where we're looking, if it's at our feet, our angle of depression is going to be this angle is 53 degrees. It's the angle from our sight line. It's not the inside angle. So if that angle is 53 degrees, what does that make our inside angle? Well, this is 37 degrees. Okay, now we want to decide how far away our park is. We know that the building we're standing on is 100 feet tall. So how could we do that? Well, I'm looking for this distance here. So I know this angle, this side, and this side. Well, this is opposite my angle. This is adjacent my angle. So we can use tangent to figure out how far away it is. So we're going to use the tangent of 37 degrees. It's going to be equal to the distance to the park divided by 100. So we can multiply by 100 on both sides, and we can get that x is equal to the tangent of 37 degrees times 100, or 75.36 feet. Awesome. Now that didn't take into account how tall we are. So let's say, for example, our guy is 6 feet tall. I am nowhere near that tall, but let's assume that it is just for the sake of this problem. So if we're actually doing this a second time, what we're doing is his line of sight is actually coming from here, and we're looking down this way. So if this is 53 degrees, this height that we're looking at, this new triangle that's created, this blue one, the height of the building is not 100 feet, but in fact, it's 106 feet. So how does that affect our problem? Well, let's take a look. We're still going to use that same tangent of 37 degrees. But now it's going to be equal to x over 106. So how does that 6 feet affect it? Well, we can multiply by 106 on both sides and solve for x, and we end up getting x is equal to 106 times the tangent of 37, which is equal to 79.88 feet. Now, why does this matter? Well, it depends on what you're trying to do. If you are just talking about in general, how far away is that park? I don't really think it matters to you whether it's 75 feet or 79 feet. It doesn't matter. However, if you're working in construction, you're trying to build a staircase, you're doing something like that where the distance that you have really does matter, you want to make sure that you're taking into account every element of this. So notice 4 feet would make a huge difference if you're building a bridge on whether or not you make it all the way across the road. right? So we want to make sure that we're being aware of when we need to take it into account and when we don't. For the sake of the assignments that we're working on or the lessons we're doing, you do not have to take it into account. And so I'm not going to, especially because it doesn't specify how tall the person is. If it does specify how tall the person is, we want to make sure that we include that so that we're being consistent. Let's take a look at one last question that involves angles of elevation and angles of depression. In this one, you're hiking and you come to a cliff at the edge of a ravine. Ooh, let's draw our picture here. So here's my cliff. I'm hiking and there is a ravine down here. My campsite is 500 meters away from the base of the cliff. So let's take a look. Here's my campsite. It's over here. Cute little campsite. And this distance here is 500 feet away, or 500 feet. That's not very far. 500 meters. We're pretty far away from that ravine there, right? We may maybe have some boulders. I don't know what kind of picture you want to draw. It says the angle of depression that you're looking from is 25 degrees. How tall is this cliff? So how tall did we just go? Well, I'm going to go from the base of my cliff, like I said, because we don't know our height. This is where we're starting at. And we just determined that our angle of elevation, or the degrees that we're looking down, is 25 degrees. So what that means is we need to find this angle to determine how tall our cliff is. So remember, that angle of depression with the top angle of the triangle that's created are complementary. So we can take the angle of depression and subtract it from 90 to figure out what's inside here. So this angle on the inside is going to be 65 degrees. Now we're looking for x. We know the opposite and we're trying to find the adjacent. So what can we do? Well, opposite and adjacent relate to tangent. Notice here how a lot of the problems that we do when it comes to angles of elevation and depression involve tangent. And the reason why is because a lot of the time we don't really care about how far my eyesight is taking me. We don't really care about that hypotenuse, but we care about how tall we are or how far away the base is from that, which are the legs of our right triangle. So we're going to use tangent a lot here. We've got the tangent of 65 degrees is equal to opposite over the adjacent side. Now we just need to solve for our adjacent side. So here I'm going to multiply by x on both sides and get x times the tangent of 65 degrees is equal to 500. And then I'm going to divide by the tangent of 65. Remember, the tangent of 65 is a number, so we do need to divide it on both sides, just like we have to do anything in an equation to both sides. These simplify, so x is equal to 500 divided by the tangent of 65 degrees. And we might be asking ourselves, what is that? Well, 500 divided by the tangent of 65 degrees is approximately 233.15 feet. Or meters, not feet, meters. So that's pretty tall. I mean, if you think about it, there's a little bit over 3 feet in a meter. So we just climbed up like over a 700-foot tall cliff. That's pretty awesome. So that is how angles of elevation and depression work. Again, an angle of depression is not the inside angle of our triangle, but it's the angle that we depress from the straight across line. So it's complementary with that inside angle. The angle of elevation is included within our triangle, however. If you have any questions, feel free to ask, but that is angles of elevation and depression and how we can use trig functions in order to solve them.